What about you? In the garage today we have a Hyundai i30, 115,000 miles on the clock. I think it's about a 2012 model. Customer complaint is engine management light is on and the car runs like. Well, I don't know where it's going to come out on the microphone, but you know, it's clearly missing, and the engine's shaking about a wee bit. Engine off, and we'll do a quick scan, as Sandy would say. Cylinder 2 Misfire, that's just in OBD there. So 4 coil unplugs, and we'll give it a go with this thing. See what it says. Oh, it's getting it. Pen where I put it. Might have just completely failed. Just turn the sensitivity down a wee bit. Not very bad. What does this thing turn the injectors off? Now, there's no sensitivity in this wee magnetic pickup, so it's picking it up there. So it may not have completely failed, but the you just see it flashing there. Yeah, the injector's flashing. On 2. Okay, on the 2 suspect, so we'll just mark it with a dot. And we'll just, we'll do the old common trick of swapping the coils over. So we'll put the one with the dot into 3. So there's our one with the dot. We'll swap her over and clear the codes and see if the fault is moved. Right, here we go. So we just have to keep adjusting the sensitivity on that wee wheel there. But yeah, fault was definitely shifted. Let's see if there's any fault codes. It's on the 3. Fault shifted. Faulty coil pack. So this coil pack, it's just a pretty basic, that's our field one with a dot on it. It's pretty basic 2-wire arrangement. This is our new one, a Hella, with a 2-wire arrangement, and we'll get that in. So that's pretty much basic stuff there. You know, we'll swap the coils to see if the fault moves. A typical primary ignition waveform. This is out of this new coil pack here. So this Hella one that I put in. And just having a wee look and really just seeing if it's much the same as the rest of them. So this is our cylinder 2. Let's get the back probe in. This is the cylinder 2 where I had the Misfire on. So there are, you know, you can tell things off this. This is a primary ignition waveform. If we did a test on the secondary side, it should mirror that. So because there's only a wee 2-wire coil, we can test it quite easily. We don't have to go on the secondary side. So yeah, we'll just stick it on the cylinder 1 here. Bear with me. See if we can get a connection on cylinder 1. No, proven. Not one there. Oh, there we go. So cylinder 1. So that's the existing coil packs. And you can see slightly different in the characteristics there, here. So the new coil pack. Just go under the new coil pack there. So, yeah. There's a bit of oscillation there on the new coil pack. So you can get different characteristics on these things. But yeah, the main spike there tells you a lot. You know, if that's very short, it could mean that you have a lean mixture or rich, depending on what's going on. So I'm just doing a comparison here to make sure they're all pretty much the same. So this being a 2-pin coil pack here, it's actually quite easy to get that waveform there. So all I was doing there to get that waveform, that scope, was back probed in here and in there, and that's it to get that waveform. It's also a good idea, I did this off camera, is check your spark plug, because if your spark plug looks like, let me see, here's a real bad one I took out of another car recently. Let's see if I can get that in the shot there. So high gap, this car is running lean there. So a higher kV, I've said this in the channel before, a higher kV required to jump a larger gap can be detrimental to coil pack failure. Just a basic drawing of this 2-wire coil pack. I'm not going to go into huge amount of detail. It's basically a transformer. So you have a lot more windings on the secondary side to get your, say, around 20 kV, so it can jump the spark there. Very, very low current. But the main thing about this 2-wire coil pack is the switching is done in the PCM. On a 3-wire 4-wire coil pack, you'll have this sort of arrangement here actually in the coil pack itself. So we can get a good waveform on it, because this is basically where I'm able to back probe onto here. So you're able to go onto the actual primary coil itself, whereas on a 3-wire you're not able to do that because you have this circuitry in the coil pack. So this is a transistor, which is just a power switching device, which is just switching this coil. So whenever the coil is actually switched off, you get mutual inductance into the secondary, and that allows the spark to jump. But is there any other type of systems? Yeah, there is. Regarding coil on plug, that's what we're talking about here. So there are different types of systems, but regarding coil on plug, so this document here is probably about 10 years old, this document. So it's from McLaren, as you can see. So actually, we'll just overview this a wee bit, not read the whole thing out here by any means. So in a petrol engine, the combustion air fuel mixture is initiated by a spark. Yeah, dead on. The spark needed to ignite the air fuel mixture in the combustion chamber is generated by a high voltage to the electrodes of the spark plug. The voltage required to generate the spark depends on the compression of the engine, the quality and the ratio of the air fuel mixture, and the spark plug instructions. So those things there are what we see. They're definitive parameters in getting a good combustion. It's not just the fact of a spark jumping a gap. So more than 12 kV is usually needed to ignite. In special cases, a few kV may be sufficient. A highly compressed or lean mixture may require more kV. So high compression lean mixtures need more of more voltage to jump the gap. As a rule of thumb, 25 kV. So conductive plasma is established between the electrodes of spark plug, and reduced voltage about 100 volts is all that's needed to maintain it. So the duration or burn time of the spark and its related energy depend mainly on the air fuel ratio and mixture. So you can tell a wee bit from the waveform there. So the burn time is that horizontal bit that's going on after the peak. So the peak in the waveform is what I call the firing voltage. So that's the, you know, enough to make the spark occur. So the spark to jump the gap, and then the burn time is the amount of time that spark is actually on for. So yeah, so short burn time, stuff like that can tell you if it's a weak air fuel mixture and things like that. But we're not going to go into that in this video. We're not going to do a diagnosis of that waveform. But I'm sure there's millions of YouTube videos about that can do that. Anyway, it goes on here. Capacitor discharge ignition or transistorized ignition. So clearly from the whiteboard there, we saw the transistorized ignition. This coil pack that we'll have down here is operated via a transistor, which is just a switch. It's a power switching device. It just switches it on and off. So both ignition switches have advantages and disadvantages. The capacitor discharge ignition, you probably, this is like a high performance thing, you know, and it's a lot more expensive way of doing it. There's higher voltages involved and stuff like that, but we'll just go into it and show you what I'm on about. And just the fact that these alternatives exist. The energy of spark is generated by an electronic circuit that stores energy at several hundred volts with a capacitor. And the moment of ignition, the energy is transferred from the capacitor to the ignition coil. Because the combustion chamber is under pressure at the moment of ignition, the coil has to transform the capacitor voltage up to several thousand volts to generate the spark. This requires the coil with a winding ratio of approximately 500 to 1, good magnetic coupling and all that there. So most CDI systems require a capacitor up to 400 volts. Energy of 50 millijoules, historical value based on that typical voltage, blah blah blah. A bulky and heavy electronic package is required to charge that amount of energy in the storage capacitor. However, McLaren Electronics has developed a system that can do that in a very short time, 500 microseconds. So yeah, as I say, you probably won't see that. And that's basically it. So you still have the windings, but it's switched with a capacitor. And yeah, let's see if there's anything here. The voltage generated fed to spark plug follows this energy transfer. The results very rapid voltage increase, making CDI insensitive to shunt resistance. Example, weak wet spark plugs. So advantages with that system, clearly a lot more expensive. On to our transistorized ignition, which is the common one here. It's very simple. Voltage is connected to ignition coil, results as current flow and magnetic energy storage in the coil. When the current is switched off, so it's switched off, I think I mentioned that, the collapse of the magnetic field in the primary coil induces a voltage in the secondary. The ratio of the turns, blah, 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 means that the output voltage is much higher than the input voltage. The result spark has an extended burn time, approximately up to 1 millisecond, as induction keeps the current flowing for as long as possible. So there we go, that's it in a nutshell. In its original form, was used long before the capacitor discharge. Initially it was a mechanical contact breaker to switch off the current. The mechanical switch placed a limit on the voltage generation within the coil as the current had been limited. In addition, an ignition condenser, which is basically a capacitor, had to be used to slow down the switch off process to prevent unacceptably short lifespan of the contact breaker. So I think the older guys amongst us will know what that is referring to there. So that's basically the points, you know. The seemingly simple task of replacing this contact breaker with a transistor was a major technical challenge. So this is, as I say, this document was printed maybe 10 years ago. So it's a wee bit in the past. But anyway, the transistor had to pass 6 to 8 amps, but it also had to withstand approximately 400 volts. 15 years ago, this was a major challenge to the semiconductor industry, that only a few companies could reliably manufacture these parts at a very high cost. Today, transistors are available and withstand 25 amps, 600 volts and more. Blah, blah, blah. Single monitor electronic design is very simple. The design of the coil is much more complex. Yeah. So there we go. That's a wee bit on that. So it's just ECU, high power switching circuit into the 2 coils there. So a big disadvantage here is the transistor A's coil inductance is high, coil inductance is low with the CDI system, and so the CDI system is far better in racing engines. Oh yes, I think it says it here. Let me see. The current is limited by the resistance of the coil. Increasing the number of turns in the coil has 2 effects. It increases, this is the transistor one I was talking about. Increases electrical resistance, reduces the current, increases inductance. A high inductance coil is very slow to charge, limits the number of sparks per minute. This is the reason that CDI was developed for high speed engines. So the capacitor job, is more for a racing engine type application. The transient response of a racing engine may benefit from the long burn times available with the TSI transistor type. Whilst it should always be possible to generate a good mixture of full engine load, this may not always be the case at part load. Part load is often considered to be of little interest to a racing engine, but valuable time is lost if a driver cannot effectively change gears or stabilize a car with a throttle, both of which are heavily dependent on crisp engine response. So after thousands of hours of defining coils for both systems, McLaren Electronics offer both types. This isn't an advert for McLaren there. I just came across this document which give a wee bit of explanation and all that. So it talks about electromagnetic compatibility. The transistor age one, there's a lot of interference with it, so you have to have some suppression circuits in it. High voltage and insensitivity to shunt resistance is most easily achieved using CDI. If your engine does not rely on an extended burn time, the CDI system will allow smaller coils, easier installation, potential longer lead length, faster voltage increase. The ECU demands of the TSI, some of the potential gain of a CDI can be recovered by fast, low inductance coils run at higher current levels of 25 amps compared to the mass market coils, which usually operate at about 10 amps. So there are, advanced ones of those, the transistor age ones. So anyway, thought you might find that interesting there. Just a wee quick overview of it. So anyway, hope it makes sense. Thanks for watching as ever, and maybe you got something out of it. All the best, and wow.